I can teach you how to diagnose your substitution and elimination reactions in under 25 minutes. Dig in, ninjas. Let's go. The first half step of our journey in diagnosing a substitution or elimination reaction is a quick stop to see if we have a competent leaving group in the molecule. It doesn't help us diagnose which mechanism is taking place, but before we spend our time doing that, we need to see if we have a competent leaving group that'll allow us to continue on with the mechanism, or if we don't have a competent leaving group and we just stopped because no reaction can take place. If we don't have a competent leaving group, we can't do a substitution or elimination reaction at all. I have a separate video where I go through all the possible leaving groups and tell you how to determine which ones can be leaving groups now in substitution land, which ones will be leaving groups later in carbonyl land, and which ones will never be leaving groups. If you're not comfortable with leaving groups or would like a refresher, I have that video linked down below. In general, for substitution and elimination, to be a competent leaving group, that group after it leaves needs to be a weak base with a conjugate acid pKa less than around 5 or so. This group, when it leaves, needs to have a conjugate acid with a pKa less than around 5 or so. The other very important component of being a leaving group in substitution land is that it must be attached to an sp3 hybridized carbon. If the leaving group isn't a weak enough base, and if it's not attached to an sp3 hybridized carbon, we cannot do a substitution or elimination reaction. If it is a sufficiently weak base and it is attached to an sp3 hybridized carbon, then yes, we can do the substitution and elimination reaction, and we should move on to the next steps to diagnose the other pieces of the puzzle. Let's go through some quick worked examples to see if we can spot competent leaving groups. In this first example, we have a bromine attached to an sp3 hybridized carbon. Bromine is a weak base and it's attached to an sp3 hybridized carbon, so yes, this molecule does have a competent leaving group. Our next molecule has a chlorine, which is a weak base, and it's attached to an sp3 hybridized carbon, so yes, this molecule also has a competent leaving group. We don't know which reaction we're going to be doing yet, but we know that we can continue on with our analysis. Our third example has a bromine, which is a weak base, attached to an sp2 hybridized carbon. So no, this molecule does not have a competent leaving group, cannot do any substitution or elimination reactions as we're learning them in this chapter. The next molecule has an iodide, which is the best leaving group on our list, but it is attached to the sp2 hybridized carbon of benzene. So no, this molecule does not have a competent leaving group and cannot undergo substitution or elimination reaction. This example looks odd. This entire group is one of the sulfonate leaving groups. It is a competent leaving group and it is attached to an sp3 hybridized carbon. So yes, this molecule can participate in substitution or elimination reaction. Our final example has a protonated oxygen, which is a leaving group. It leaves as water, and it's attached to an sp3 hybridized carbon. So yes, this example also has a competent leaving group. This check doesn't take very long, but it ensures that we have the ability to continue on with our analysis. Common error alert. The factor here that trips up most students is it must be attached to an sp3 hybridized carbon. Be careful that you don't accidentally try to do a substitution or elimination with the leaving group on an sp2 hybridized carbon. The first big step in diagnosing our substitution and elimination reactions is to assess the nature of the nucleophile/base. We can classify the nucleophile/base as one of several types, and once we know what type of nucleophile or base it is, that will give us evidence for certain mechanisms and evidence against certain mechanisms. Let me go ahead and say right here at the outset, we cannot fully diagnose a reaction based only on one dimension. We can't only look at the nucleophile or base and decide exactly what reaction is going to take place. We have to go through all of these steps I'm about to lay out. So what is it about the nucleophile or base that will allow us to predict these reactions? First, let's look at the mechanisms from the perspective of the nucleophile or base. In an SN2 mechanism, the nucleophile uses its lone pair to directly attack the electrophilic carbon, directly kicking out the leaving group, giving us our substituted product. In an E2 reaction, the base uses its lone pair to directly attack the beta hydrogen, breaking the carbon-hydrogen bond, forming the alkene, and directly kicking out the leaving group, forming our alkene product. From the perspective of the nucleophile or base, the SN1 and E1 reactions work a little bit differently. For the SN1 reaction, the nucleophile doesn't do anything in the first step. It is a spectator in the rate-determining step, as the leaving group leaves to form the carbocation. Then, the nucleophile can use its lone pair of electrons to form a bond with the electrophilic carbocation. In the E1 reaction, the same thing happens. The leaving group spontaneously leaves to form the carbocation. Then, the base can use its lone pairs to take the beta hydrogen and form the double bond in our product. So just by looking at these generic conditions, we can already start to see some personality differences in the nucleophiles and bases for the various reactions. In the two-type reactions, the nucleophile and base needs to be strong enough to directly get in there and directly attack the electrophilic carbon or directly attack that beta hydrogen to form the product immediately. It's going to need to be a very strong nucleophile or a very strong base to have enough inherent energy to directly get in there and do the reaction. The one-type reactions, in contrast, the nucleophile and base must not be strong enough to directly attack. How do I know that? Because if it was strong enough to directly attack, it would have just done an SN2 reaction. So for the SN1 reaction, we must have a weaker type nucleophile that has to wait around for the carbocation to form, Then the nucleophile can swoop in and make the product. In the E1 reaction, the base must be a weak base that has to wait around for the leaving group to leave to form the carbocation before we can do the elimination. If it was a strong base, it would have just done the E2 elimination directly. So that's our first step. We need to classify the nucleophile and base as either a strong nucleophile, strong base, weak nucleophile, or weak base. So how do we do that? Great question. Thanks for asking. To be a strong nucleophile and a strong base, we need a lot of inherent energy packed in a very small volume, probably a full negative charge. We can recognize strong nucleophiles and strong bases because they have a conjugate acid pKa between 15 and 25. Bases don't have pKa's, but their conjugate acids do. And if the conjugate acid is between 15 and 25, that would classify that molecule as a strong nucleophile, strong base. These would include molecules like hydroxide, or really any alkoxide. It doesn't really matter what alkyl group the R group is. The conjugate acid would be an alcohol, which would have a conjugate acid pKa between 15 and 25. Other examples of strong nucleophiles and strong bases would be the acetylide anion, the conjugate base of an alkyne, and the enolate anion. You may not have gotten to enolates yet. Don't worry about it. Put it on this list. When you see it, you'll know. Our next category is weak nucleophiles and strong bases. What would make something a strong base, but not a very good nucleophile? There's two factors why this might be so. The first is if the molecule is very sterically bulky, then it might be too sterically big to do a nucleophile reaction, but it can still act as a base. The other factor that would make a molecule a weak nucleophile and a strong base is if it has a conjugate acid pKa that is greater than 25. These types of molecules will be such strong bases that they're effectively bad nucleophiles. The only thing they can do is base things because they are such a strong base. Examples of molecules that are weak nucleophiles and strong bases include the most prototypical example in this class, and that is the T-butoxide anion. It's often paired with potassium as the countercation. Potassium T-butoxide has all this steric bulk in these three methyl groups, making it so sterically bulky that it can't really be a nucleophile, but it is still a good base. The other example that we don't see very often is a molecule called DBU. The molecule DBU is very hard to draw. You should see the outtakes between that jump cut. It's a 7-ring fused to a 6-ring with 2 nitrogens in that ring. It's quite sterically bulky, can't be a nucleophile, but it is a good base. Examples of molecules that are such strong bases that they're not nucleophiles include things like sodium hydride, sodium plus H minus. H minus is the conjugate base of H2, which has a pKa of around 35, so that's definitely greater than 25. We would also include deprotonated ammonia. The conjugate acid of NH2 minus is NH3 ammonia, which also has a pKa of around 35 or 38. In fact, any deprotonated amine would fit into this category, including a very common base that we see later in this course, lithium diisopropyl amide, which goes by the abbreviation LDA. All of these are such strong bases that they're not good nucleophiles. Molecules that are strong nucleophiles but weak bases have a lot of electron density, a full negative charge. They're just not very strong bases. These would include anions that have a conjugate acid pKa less than about 10 or so. These would include molecules like the halide anions. It would also include HS minus, or really any deprotonated thiol. In that respect, they're very similar to OH minus and RO minus, except thiols have a pKa of around 10. Other nucleophiles you might see here include cyanide, CN minus, and azide, N3-. That's an odd-looking nucleophile. The one negative and positive cancel each other out, and the other negative is the nucleophilic nitrogen. Our last category is weak nucleophiles and weak bases. These are conjugate bases of strong acids that just don't have enough electron density to be a strong nucleophile. These are molecules that are pretty stable on their own. Yeah, they've got a lone pair. They're a nucleophile, but they don't have a full negative charge or anything. These are neutral molecules with a conjugate acid pKa less than around 4 or so. These would include neutral molecules like water, or really any alcohol. They would also include neutral carboxylic acids. The other one I'm going to put on this list is a carboxylate. You might wonder why a carboxylate goes in this list. It has a negative charge. Why is it a weak nucleophile, weak base? The carboxylate is the conjugate base of a carboxylic acid, which has a pKa of around 4 or less, so it can't be a strong base. And this negative charge is stabilized by resonance with the other oxygen, so the negative charge is not a strong nucleophile. So because it's a weak stabilized molecule stabilized through resonance, it is a weak nucleophile, weak base. These are the most common nucleophiles and bases you're going to see in substitution and elimination land. You need to be able to turn the page, look at the nucleophile, and identify it in one of these 4 categories by sight. Once we've classified the nucleophile or base in one of these categories, we can start using it to predict the outcome of the reaction. If the molecule is a strong nucleophile and strong base, then it has lots of electron density in a very small volume. It's very energetic, very reactive, and yes, it does have enough energy to directly get in there and attack the electrophile. That means strong nucleophile and strong bases are evidence for SN2 and E2 reactions. These require the nucleophile and base to be strong and have enough energy to directly get in there and attack. That means they are evidence against SN1 and E1 mechanisms. If we have a weak nucleophile strong base, these will be evidence really only for E2 reaction, and evidence against an SN1, SN2, and E1 mechanism. But wait, you might be asking, why is it evidence against an SN1 reaction? It's a weak nucleophile, and that's a very good point. It is a weak nucleophile. It will have to wait around for a carbocation if it wants to do a substitution reaction, but it won't. It's a strong base. It will directly attack the beta hydrogen to form the alkene in the E2 reaction long before it has to wait around for a carbocation to form. If we identify the nucleophile as a strong nucleophile and weak base, that will be evidence for an SN2 reaction and against an SN1, E1, and E2 reaction. If you're wondering why we classify it as a weak base, but it's evidence against an E1 reaction, it's the same conversation we just had. It's such a strong nucleophile that it won't wait around for a carbocation to form. It will get in there and directly attack that carbon with the leaving group, doing the substitution preferentially. Our last category is weak nucleophile and weak base. Weak nucleophile, weak base is an evidence for an SN1 and an E1 reaction, and evidence against an SN2 and an E2 reaction. It is not strong enough to get in there and directly attack. It will have to wait around for the carbocation to form. Once the carbocation forms, it can really do SN1 and E1 without much preference. Unless we have some other controlling factor, we tend to get mixtures of SN1 and E1 products when we have a weak nucleophile and weak base. This is one dimension of our analysis. We can't stop here. We have to move on to the next step. The second dimension we must analyze is the nature of the electrophile. We classify electrophiles based on their degree of substitution as either methyl, primary, secondary, or tertiary. This isn't a video about degrees of substitution. If you'd like a refresher, I have that video linked down below. In short, the degree of substitution of a leaving group is the same as the degree of substitution as the carbon to which it is attached. So this carbon is a secondary carbon. It's attached to two other carbons. That makes this leaving group, this electrophile, a secondary electrophile. This carbon is attached to three other carbons. That makes this a tertiary electrophile. And this carbon is only attached to one other carbon. That makes this a primary electrophile. Pause the video, see if you can identify the degrees of substitution for the electrophiles in this molecule. This iodide is a tertiary iodide, this chloride is a secondary chloride, and this bromide is a primary bromide. Now, when the leaving group is attached to a carbon that's not attached to any other carbon, we call this type of electrophile a methyl electrophile. The leaving group is attached to a methyl group. So why does the degree of substitution impact what kinds of mechanisms we can do? Let's take a look at these examples and see if we can figure out how these examples give us clues about what types of mechanisms they can and cannot pursue. If we look at a methyl electrophile and we think about the elimination reactions, to do an elimination reaction we need to remove a hydrogen from the beta carbon, but there is no beta carbon. If there is no beta carbon, we can't do any elimination reactions. Methyl electrophiles cannot do any elimination reactions, not E1 or E2. So when you see a methyl electrophile, you can look at it and say, there's no second carbon, I can't do an elimination. If we look at these carbocations, this is a methyl carbocation and this is a primary carbocation. They would form when the leaving group leaves from a methyl electrophile or from a primary electrophile. Methyl and primary carbocations are exceedingly unstable. They don't have enough hyperconjugation to stabilize that positive charge. If you'd like to brush up on carbocation stability and hyperconjugation, I have a link to that video down below. The SN1 reaction and the E1 reaction both go through carbocation intermediates. If we can't form a methyl or a primary carbocation, then a methyl electrophile and a primary electrophile cannot do any of the carbocation reactions. That means no SN1 and no E1. If we can't form the carbocation, we can't do the mechanism. Finally, if we look at this tertiary electrophile, what I want you to notice is the three alkyl groups around that electrophilic carbon. To do an SN2 reaction, a nucleophile has to get close enough to this carbon to form a new bond with that carbon. But there's a problem with tertiary electrophiles. Do you see how large they are? And these are just methyl groups. These large alkyl groups, three of them are blocking access to that carbon for the nucleophile to attack. They are causing a lot of steric hindrance around that electrophilic carbon, making it effectively impossible for that nucleophile to swim in and try and get close enough to that carbon to form a bond. It's just physically blocked by the three alkyl groups in a tertiary electrophile. So if a tertiary electrophile is too sterically hindered for that nucleophile to get in there and attack, that means a tertiary electrophile cannot do an SN2 reaction. With these limitations in mind, we're ready to diagnose the electrophile. The electrophile could be a methyl electrophile. A methyl electrophile can't form a carbocation, and it doesn't have a beta carbon. So it can really only do an SN2 reaction. It's evidence against an SN1, an E1, and an E2. It's evidence against the 1 reactions because we can't form the carbocation, and it's evidence against the E reactions because it doesn't have a beta carbon. Our electrophile could be a primary electrophile. Primary electrophiles can't form primary carbocations, but they can do SN2 reactions and E2 reactions. They just lack the ability to do SN1 reactions or E1 reactions. Our electrophile could be a secondary electrophile. A secondary electrophile can form a carbocation, and it does have a beta carbon, and it is not too sterically hindered. So a secondary electrophile can do an SN1 reaction, an SN2 reaction, an E1 reaction, or an E2 reaction. And it is evidence against none of the reactions. That's right, the secondary electrophile can do them all. It doesn't help us determine which of the 4 mechanisms are in play. We'll have to use other evidence to decide if we have a secondary electrophile. Finally, we could have a tertiary electrophile. Can you tell me why we can't have a quaternary electrophile? The tertiary electrophile is too sterically hindered for an SN2 reaction, but it does have a beta carbon, so we can do eliminations. And tertiary carbocations are fantastic carbocations, so we can do an SN1 reaction, an E1 reaction or an E2 reaction. The tertiary electrophile, though, is evidence against an SN2 mechanism. The nucleophile gives us evidence for and against certain mechanisms. The electrophile gives us evidence for and against certain mechanisms. The last piece of evidence is the solvent. You might not consider the solvent very important. It's just the stuff that dissolves everything. But the solvent we choose can interact with the nucleophile and can drastically change the course of the reaction. Solvents are generally classified into one of three categories: nonpolar, polar protic, or polar aprotic. Nonpolar solvents are solvents that don't have a polar bond. They would include things like hexanes, benzene, and toluene. Although I gotta tell you, these are not very green solvents from a green chemistry perspective. They're highly flammable and highly toxic. There actually aren't a lot of great choices in terms of green chemistry non-polar solvents. The closest that we get is heptane. It's still flammable, but it's not as toxic as the other solvents. We don't see non-polar solvents in this unit very often, and that's because they don't do a very good job dissolving our reagents. Our nucleophiles and electrophiles are typically polar or sometimes ionic salts, and they just don't dissolve in non-polar solvents very well. So we don't see these very often. Polar protic solvents are solvents that have a polar bond and protic. What does protic mean? Protic means the solvent has a hydrogen capable of hydrogen bonding. The most prototypical is water. Water is polar and has a hydrogen capable of hydrogen bonding. Most small alcohols, as long as they are liquids, are also polar protic solvents. And sometimes you'll see a carboxylic acid, as long as it is also a liquid, it is a polar protic solvent. In terms of green chemistry, these actually aren't that bad. Water is a very green solvent. Most alcohols are okay as green solvents, but the green chemistry solvent that fits into this category is a molecule called ethyl lactate. It is a green chemistry version of a polar protic solvent. Polar aprotic solvents are solvents that have polar bonds but do not have a hydrogen capable of hydrogen bonding. We mostly recognize polar aprotic solvents because they tend to go by acronyms. Prototypical examples include tetrahydrofuran, THF, dimethyl sulfoxide, DMSO, acetone, dimethylformamide, DMF, and acetonitrile, MECN. Most of these solvents are pretty flammable and have some toxicity issues. More preferred green chemistry solvents include cyclopentyl methyl ether, CPME, or ethyl acetate, ETOAC. Why does this matter? It matters because these solvents can interact with the nucleophiles in our reactions and attenuate the nucleophilicity of that molecule. It can make some nucleophiles stronger nucleophiles and some nucleophiles weaker nucleophiles. Let's take, for instance, Br- as a nucleophile. And let's say it's in a polar protic solvent like methanol. In a polar protic solvent like methanol, bromine can use its electron density to form hydrogen bonds with the protic hydrogens of methanol. Remember, that's what it means to be a polar protic solvent. What does that do? It takes the electron density on bromine and it spreads it out over a larger volume through these hydrogen bonds. Anything to spread electron density out over a larger volume makes that part of the molecule more stable, and anything to make part of a molecule stable makes the whole molecule more stable. So nucleophiles that are highly solvated by polar protic solvents are weaker nucleophiles than we would otherwise expect because they don't have as much electron density around that nucleophilic atom. They make nucleophiles weaker. If we look at that same bromide nucleophile in acetone as a solvent, the partial positives of the acetone polar bond will line up with the bromide negative charge, but we can't stabilize this negative charge with any hydrogen bonds. In fact, we can't even really stabilize the Br- with sodium-. The sodium- is hanging out over here by the oxygen partial negative, and it's sequestering that bromine all by itself inside the solvation sphere. It's taking all that electron density on bromine and smashing it down and concentrating it into an even smaller volume than it was before. That's going to make bromide even more reactive and an even stronger nucleophile than it once was. Polar aprotic solvents make nucleophiles stronger. So in terms of deriving the evidence from these various types of solvents, we're either going to be dealing with polar protic solvents or polar aprotic solvents. Since nonpolar solvents don't dissolve these molecules, we don't really use them in these reactions. Polar protic solvents weaken nucleophilicity a lot, but don't weaken basicity quite as much. As a weaker nucleophile, this is going to be evidence for SN1, and it's also going to be evidence for both eliminations. It doesn't weaken basicity as much as nucleophilicity. In terms of evidence against, this is evidence against nothing. Very important point here. We don't use solvents as evidence against any of our mechanisms. It may push us in favor of certain mechanisms, but it doesn't preclude us from doing a certain mechanism. There are all sorts of examples of SN2 reactions being done in ethanol. It may weaken the nucleophile, but it can't preclude any certain mechanism. So we never use solvents as evidence against mechanisms. Polar aprotic solvents make nucleophiles stronger and give us evidence for SN2 reactions. But again, we don't use solvents as evidence against any of our mechanisms. In this respect, you can think of solvents almost like tiebreakers. If the nucleophile and electrophile can't agree on which mechanism is going to occur, the solvent can often break that tie. In that vein, there's one other thing I'm going to include on this list, and that is heat, elevated temperature, the delta symbol. Elevating the temperature increases the T delta S term of our Gibbs free energy equation. By increasing the impact of entropy, raising the temperature will favor reactions that form more products. And in elimination reactions, we start with 2 molecules and end with 3. Because elevating the temperature impacts that entropy term, adding heat to a reaction favors the E1 and E2 reactions, but again, we won't use this as evidence against any of our mechanisms. Heat doesn't preclude us from doing a certain mechanism. Okay, that's it. We have all of the information we need now. We can successfully diagnose the substitution or elimination reaction. You can't skip any steps. You have to assess the nucleophile, the electrophile, and the solvent, put it all together, and see what the preponderance of evidence tells you about the mechanism. Let's do an example. I like to make an NES table for these reactions. I would suggest you do the same. This allows you to organize the information for the nucleophile, the electrophile, and solvent and see what the evidence suggests. So let's look at our nucleophile. The nucleophile is sodium methoxide. Oftentimes, students will look at this and think that it's a weak nucleophile, but it's not. Remember, sodium doesn't make covalent bonds, so this is sodium positive and OMe negative. As OMe negative, that fits the OR minus type of nucleophile, and that makes it a strong nucleophile and strong base. It has enough energy to do the SN2 and E2 mechanisms, so it won't wait around for a carbocation to form for an SN1 or E1 mechanism. Our electrophile is a primary electrophile. We can't form a carbocation at a primary carbon, but we can do an SN2 or an E2 reaction. We just won't be able to do an SN1 or an E1 reaction. Our solvent is THF, that's one of the acronyms. This is a polar aprotic solvent. It makes the nucleophile stronger, an evidence for an SN2 mechanism. And remember, we don't use solvents as evidence against any of our mechanisms. If we look at the nucleophile and electrophile, they don't really have a preference for SN2 or E2. But our solvent is evidence for SN2. The preponderance of evidence says that this mechanism will be an SN2 mechanism. Our good, strong anionic nucleophile can directly attack the electrophilic carbon, directly displace the leaving group to form our product. And we get the SN2 product as our major product. The other choice would have been the E2 product. Will we ever form the E2 product? Yeah, probably, sometimes. This is a strong nucleophile and a strong base. It can take the beta hydrogen to form the alkene, but our solvent strengthens the nucleophile and favors SN2, and I don't see elevated temperature to favor the elimination. So the SN2 product will for sure be our major product, and the E2 product would be a minor product in this reaction. Had our solvent been different, had we added elevated temperature, we could have made the elimination our major product. This is why it's so important to assess all three dimensions of the reaction before you make your decision. If you were to analyze the product mixture, maybe you've learned about GC mass spec, you would see the SN2 product as the major product, but I wouldn't be surprised if there was a peak for the minor elimination product. On an exam setting, you're going to have to be very careful about reading the directions for the question. Most of the time, your instructor will say, draw the major organic product of the reaction. But be careful. If the instructions say, draw all possible products, then you would want to list both the SN2 and the E2, because both are mechanistically legal, and label them major and minor. Whew. We did it. We crammed a lot into a very short amount of time, but you have a very solid foundation for diagnosing your substitution and elimination reaction. Go be an OChemNinja.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.